Chapter 6 covers the Hibernation module and low power modes. This module manages the removal and restoration of power to the CPU and peripherals to provide a means of reducing the power consumption. Additional features include a real-time clock that can be used for wake events and battery-backed SRAM for storing and restoring the processor state. Some key features of the Hibernation module. The real-time clock is a 32-bit seconds counter with a 15-bit sub-seconds counter, so you can time much lower than single seconds. And it has an add-in trim capability for getting precision control over the time. We have a dedicated pin for waking up using an external signal. The real-time clock is operational, and the Hibernation memory is valid as long as the battery voltage is valid. Now, on the LaunchPad board, the battery voltage is connected directly to the processor voltage, so the battery voltage will never be bad. But in your design, you may have a separate battery and a separate battery holder. So if that battery is dead or if that battery is not present, you don't want your part going into hibernation. The part will not go into hibernation as if that battery isn't there or isn't valid. We also have a VDD3 on mode that provides state retention of the GPIO pins during hibernation. Remember that what's going on here is we're actually shutting the part off at the very lowest power modes. When that happens, you're essentially coming back up from reset. This will allow you to keep the GPIO pins there as you come back up without resetting them. So if you're going to shut the part down, you need a mechanism for power control. We have an on-chip voltage regulator for doing that power control for the CPU only. We also have a pin that comes out to provide system power control through a voltage regulator on your board for any other onboard hardware. The part has low battery detection, signaling, and interrupt generation with optional wake on low battery. If that battery gets down to the point where it can't run anymore, it can't hold your memory in place, you probably want to wake up. You can connect a 32,768 Hertz external crystal or an external oscillator clock for the real-time clock. There are 16 32-bit words of battery-backed memory for you to save the processor state to during hibernation. It's important here, this is battery-backed SRAM. Other types of memory like EEPROM or flash have significant issues if you power down the device as you're trying to save things in them. One, it's slow to write to those things, and two, they eat a lot of memory. Three, there's a big problem if you power down in the middle of actually trying to write those things. Battery-backed SRAM doesn't have any of those issues. It's extremely fast, it's extremely power efficient, and if you actually manage to power down in the middle of it, all you end up with is a corrupted saved piece of memory. You don't end up with corrupted memory. We have programmable interrupts on the module for real-time clock match. You can wake every 3 seconds, 10 seconds, and so on. We can wake on an external pin, and we can wake on low battery events. The power modes on the LM4F are run mode, sleep mode, deep sleep mode, and then the hibernate modes below that. VDD3 on with the real-time clock running and without the real-time clock running. Now anytime you quote these kinds of numbers, you need to be asking under what conditions are these numbers valid. In these numbers were done at 40 megahertz with the PLL on for the run mode and the sleep mode. You'll take a look on the next page, will give you some further details on this. But whenever you're looking at the strict numbers on what the current consumption is, you really need to be aware of under what conditions these numbers were derived. So the run mode, we're looking at somewhere in the 32 milliamp range. When we go into sleep mode, that's going to stop the processor clock. Of course, turn off that means basically the processor is not running, it's still powered. So a 2 sys clock wake up time, a significant power savings, and a very fast wake up time. When you go into deep sleep mode, that stops the system clock and switches off the 400 megahertz phase lock loop and flash memory. You're still getting a 1.25 to 350 microsecond wake up time, which is pretty fast. We're still coming up with the numbers on the exact current draw for those. Hibernate modes. There are three different kinds of hibernate modes here. In the Hibernate VDD3 on, this can be with the power on or on battery. The hibernate modes RTC and no RTC are only on battery. These are going to give you in the 500 microseconds wake up time to come back up from very, very deep sleep. Down into 5 microamps, 1.7 microamps, and 1.6 microamps. Let's take a look at a few more details about the power modes on the next slide. Next up is a power mode comparison. Now, critical to any power mode comparison is always the asterisk at the bottom, right? Under what condition are you making these measurements? Here you can see we're taking a look at the run mode, sleep mode, deep sleep mode, the VDD3 on mode, and then we have hibernation mode with the real-time clock running, and hibernation mode without the real-time clock. So as far as the power goes, we're running the part at 3.3 volts, and that applies all the way until you're in the deep hibernation, the two deep hibernation modes on the far right. In those, the VDD will be off. The VBAT doesn't matter until you reach any of the hibernation modes. The battery voltage needs to be 3 volts. The system clock down here, when we're in run mode, it's 40 megahertz with the 400 megahertz phase lock loop running in there, and in the sleep mode. In deep sleep mode, we're running the part off of the low frequency oscillator on the part. In any of the hibernation modes, the system clock is off. Take a look at the core parameter down here. In the run mode, sleep mode, and deep sleep, the core is powered on. In the others, it's off. The core is clocked in run mode, not clocked in any of the rest of the modes that we're using here. You can see that only in run mode will we have all the peripherals on. And here, what are we doing during the run mode? We're actually in a while loop. We're actually running some code that's off and doing something. Be careful about what you see there. Some processors may be sitting there doing nothing. This is actually in a while loop. And the other ones, it doesn't matter because the core isn't clocked, so it can't run any code. Now this box, this red dotted box, denotes the power modes that are available on the LaunchPad board. That's because we don't have a battery on the LaunchPad board. The VBAT is connected to the CPU voltage, which means we can't run those hibernation modes on the far right. Your system could run that. Certainly the LM4F120H5QR could run that if that battery voltage was pin was connected to a battery. So in run mode, we're seeing 32 milliamps at 40 megahertz core speed. In the sleep mode, 10 milliamps with 40 megahertz and the PLL running. The deep sleep mode, we need to get a number on that. That's still under investigation. The hibernation mode is down in the 5 microamp range. We'll be able to measure that in the class. Hibernation mode off the battery with a real-time clock running is somewhere in the 1.7 microamp range. Hibernation without the real-time clock running is somewhere in the 1.6 microamp range. Those are extremely good numbers for an ARM device. So like I mentioned on the previous slide, the low-cost LaunchPad board doesn't have a battery holder. The VDD, the power to the CPU, and the V battery are wired together on the board, so that's going to disable those battery-only powered low-power modes. So if you take a look at the diagram here on the bottom, you can see that the pin 37, the VBAT, is connected to the analog voltage as well as the 4 VDD pins. Now those are connected to the pins H24 and H25. Right now on the top of your board you'll see a jumper. That jumper jumpers those pins together. R30 has been omitted. We will be able to use our meter to measure the current between those two pins. I'd like to highlight though, most meters have a problem in terms of the equivalent series resistance. If you're in a very low power mode, say trying to measure 200 microamps or less, you usually can't get enough current say 30 or 40 milliamps, you can't get that through the meter, so the equivalent series resistance is too high. The other thing is that when you plug these things on there, you will probably want a set of leads that are able to go over top of the Molex connector, or you have some kind of a clip. Trying to hold probes onto the top of these things just doesn't work. In Lab 6, you're going to measure the current draw of the LM4F device when it is placed in run and hibernate modes. The low-cost Stellaris LaunchPad board does not have a battery holder, so the battery power input is connected to the power for the CPU. This will shorten our experiment somewhat, but you'll still see the device wake up from the real-time clock and wake pin events. In Lab 6, Step 1, we've already created the Lab 6 project for you with an empty main.c, a startup file, and all the necessary project and build options set. Maximize Code Composer Studio and click Project, import existing CCS Eclipse project, make the settings shown below to import Lab 6, and click Finish. You'll notice that this time we just said Lab 6 there. We're for the search select directory, and Code Composer managed to find the entire correct projects. If you had multiple different kinds of projects, it would have offered that to you as well. Some limitations here. In Step 2, in order to keep the cost of the LaunchPad board ultra low, the battery holder was omitted. So we'll be evaluating the following power modes and wake events out of the full set. We're going to take a look at what the current is in run. We're going to take a look at what the current is during hibernate. That's the VDD3 on hibernate mode. We're going to do a wake from pin without the RTC, and then we're going to do a wake from RTC, RTC being real-time clock. So the first thing we need to do in Step 3 is to open main.c for editing and delete its current contents. Type or copy-paste the following lines in the main.c to include the header files needed to access all the Stellarisware APIs. Notice that we've added hibernate.h to the list. Then in Step 4, again, performing error checking on function calls is always good programming practice. Skip a line after the previous includes and add the following code. Debug, the predefined symbol, has already been added to the project's predefined symbols. In Step 5, skip a line and add the main template after the error function. Next up, Step 6, configure the system clock to 40 megahertz again. Add this line as the first line of code in main. In Step 7, we're going to use the green LED. Remember, 2 equals red, that's pin 1. 4 equals blue, that's pin 2. 8 equals green, that's pin 3. So we're going to use the green LED as an indicator that the device is in hibernation. The LED will be off for hibernate and on for wake. Add a line for spacing and add these lines of code after the last. You should recognize that this is enabling the port F peripheral, changing the pin type for all 3 of the output pins to output, and then writing an 8 to GPIO pin 3. That means that single one will light that green LED. In Step 8, we want to set the wake condition to the wake pin. Take a look at the board schematics and see how the wake pin is connected to user push button 2, that's SW2 on the LaunchPad board. So we have a total of 6 lines that we're going to be dropping in here. The code has the following functions. The very first line is the syscontrol peripheral enable. Obviously that's to turn on, make sure the hibernation module is turned on. Line 2 is the hibernate enable EXP clock. That defines the clock supplied to the hibernate module. Line 3, calling this function enables the GPIO pin state to be maintained during hibernation and remain active when waking from hibernation. That's pretty much the definition of the VDD3 on mode. Pin 4 is a delay. We're going to delay about 4 seconds so that you can observe the LED. Line 5, we're going to set the wake condition to the wake pin. So you can see hibernate, wake, set. It says hibernate, wake pin. So that's what we'll wake on. In step 6, we're going to turn off the green LED right before the device goes to sleep. In step 9, finally, we need to go into hibernation mode. This is with the Hibernate request API function call. That function requests the Hibernate module to disable the external regulator, removing power from the processor and all its peripherals. The hibernation module remains powered from the battery or the auxiliary power supply. Remember, in our case on the LaunchPad board, that will be powered from the VDD. If the battery voltage is low, or if your battery isn't present, or if interrupts are currently being serviced, the switch to hibernation mode may be delayed. If the battery voltage isn't present, the switch may never occur. That's a good thing. You don't want your device going to sleep if it can't wake up. The while loop underneath the hibernate request acts as a trap while any pending peripheral activities shut down or other conditions exist. Add a line for spacing, and then add these 4 lines after the last ones in main. Click your Save button to save your work. Take a look in the workbook. Your code should look something like you see there. That code is saved in the Lab 6 CCS folder as main1.txt. Don't forget, you can autocorrect the indentations if you see any errors. In step 10, compile and download your application by clicking the debug button on the menu bar. If you have any issues, correct them and then click the debug button again. After a successful build, the CCS debug perspective will appear. Delete all the watch expressions by right-clicking in the expressions pane and clicking Remove All and then Yes. Now, this is a good point to bring up a note here. Code Composer Studio has some issues connecting to hibernating devices and reconnecting, since they are essentially powered off in the middle of the debugging process. So Code Composer thinks it's connected to the part, and then it's abruptly turned off. What we're going to do is we're going to try and step around those issues, but you may see, and we may see here, we may see Code Composer Studio terminate abruptly. If this happens, we can restart CCS and try again, or you can use the LM Flash programmer to reprogram your device with the Quick Start non-hibernation program. In either case, you need to hold down SW2 to keep the LM4F device awake in order for either tool to connect to it. So in step 12, what we've done now is we've downloaded Hibernate code to the part. If we were to run it at this point, the board would go to sleep while the debugger is still connected. So what we're going to do is we're going to step around the issues. We're going to press the Terminate button in Code Composer to return to the editing mode. When you do that, the LaunchPad board gets issued a reset. If you observe the LED on the board and cycle power, I'm going to cycle power on the board like this. You'll notice that the green LED stays on for about 4 seconds and then goes out, indicating that the device is in hibernate mode. I can press the SW2 switch here to wake the part. After about 4 seconds, it'll go back to sleep. Note that the wake up process, remember what's going on. When we go into hibernate mode, it's shutting the power off to the part. So the wake up process is essentially the same as powering up. We will not be using the battery-backed memory in this lab, but that feature is essential to applications that need to know how they woke up. Your code can save and restore the processor state to that memory very quickly. When your code starts, you can determine that the processor woke from sleep and restore the processor state from the battery-backed memory. In step 13, now that we know the code is running properly, we can take some current measurements. But before we do, let's comment out the line of code that lights the green LED, so the LED current is not going to be part of our measurement. In main.c, comment out the line of code GPIO pin write that writes the 8. That's the one. And save your work. Now, what's critical here is that you have to press and hold SW2 on the LaunchPad board to make sure it's awake before you try to download code to the part. And then we'll compile and download by clicking the debug button. So I'll press this, and when I do, then we'll press the debug button. Click and click. Now you'll notice that CodeComposer is back up. At this point, click the Terminate button in CCS to return to the editing mode. You'll notice that the green LED went out because from the last code. I'm going to reset the part. Now the green LED should not light at all. In step 15, I'm going to remove the connector, and I'm also going to remove the jumper here from the power measurement pins. Then I'm going to connect my digital multimeter with the positive lead nearest the device port. Great. If you want to make your own pins, these are Molex female pins that I used on this inexpensive meter that I have here. So I'm going to set the meter to measure DC current around 20 milliamps, like this. So watch the meter display, and I'll plug the USB emulator cable into the LaunchPad. Wrong one. (21.4). So after about 4 seconds, the device is going to go into the hibernate mode. So I got 21.4 for the meter reading during run, and I'll switch it down here, and I measure, let's say, 7 microamps for my VDD3 mode. So if you're keeping track in the chart on step 18, you should have whatever your reading was for the run. That's workbook step 15. Our reading was 21.4 milliamps. The next reading we got for VDD3 on, that was with no RTC. That gave us about 7 milliamps here. The reading that we got earlier was about 6 microamps. In step 19, plug the USB emulator cable back into the LaunchPad board, and I'm going to make sure that I'm fully powered here. In main.c, find the line of code that says hibernate, wake, set, hibernate, wake pin. Right above that line of code, we want to enter the 3 lines that you see in step 20. Those lines configure the RTC wake-up parameters, RTC being the real-time clock, reset the real-time clock to 0, and then turn the real-time clock on, and then set the wake-up time for 5 seconds in the future. So you can see it says hibernate RTC set, so we turn it to 0, we enable it, and then we set the match set to 5. So that's 5 seconds in the future. In step 21, we also need to change the wake-up parameter from just the wake-up pin to add to the RTC. So where we had before hibernate wake set was the hibernate wake pin, we also need to change it to, or it with hibernate under wake under RTC. And that's a great way to do it too. Uncomment the line of code that turns on the green LED as shown below. That way we'll be able to see that this works. That's in step 22. So take a look in the workbook. Your code should look very much like what we have in the workbook. If you're having problems, this code is saved as main2.txt in your Lab 6 CCS folder. In 23, we're going to press and hold the SW2 button to wake the board up to send this code back down to the evaluation board. If Code Composer can't talk to the device because it's asleep, you accidentally don't press the button, or you try to talk to a hibernating device, you will get the message that the frequency is out of range. If that happens, you can hold the SW2 button and click retry. So what I'm going to do here is I'm going to press the SW2 button to wake the board, and when I say click, then we'll click the build button to send the code down to the board. Click. And we're back up. So now, in step 24, press the terminate button in Code Composer Studio to return to the editing mode. When the debugger terminated, it reset the device. You should see, and will see, the green LED turning on for 4 seconds and then off for about 5. The real-time clock is waking the device up from hibernate mode after about 5 seconds. Also note, we can, when this device goes to sleep, I can wake the device up with SW2 at any time, since that was part of our ORD connection. So you'll also notice what I did is I changed the meter here to my maximum amount of current. If the meter is in the lowest possible setting, you will likely not be able to send data down to the board or have the LED light, since the meter, the equivalent series resistance, is too high to have the current flow through the connection here. So I have the jumper off. I still have the jumper off, and the DMM is still set up. So I'm going to double check my lead connections. Everything looks pretty much okay. I'm going to remove the USB emulator cable and plug it back in here. You can see we're still getting, even when the LED is on, it's not drawing an excessive amount of current. It's something like 21 milliamps. So when that LED goes off, I'm going to switch this down to take a meter reading at the lowest possible value of hibernation. And I get somewhere in the 10 microamp range. Okay, in step 29, to make things easier for the next lab, we're going to use the LM Flash programmer to reprogram QS-RGB, the bin file, into the device. So since we're not currently editing or debugging in Code Composer Studio, I'm going to pull a connection, disconnect my meter, turn it off, reconnect the power settings, put the USB connection back in place. See the Hibernate code is running right now. So what we'll do is we will minimize Code Composer Studio, bring up LM Flash Programmer. It should be set up to program the correct QS-RGB bin. Before we hit the program button, I need to make sure that the device is awake. So I'll press SW2, now press the program, and we're back to the original non-hibernation code. So when you're done experimenting, we can close the LM Flash Programmer, bring Code Composer back up. Go ahead and, since we've already hit the terminate button, go ahead and close the Lab 6 project and minimize Code Composer Studio. So in step 31, as a homework idea, experiment with the real-time clock to create a time of day clock
at the lowest possible power.